Hi Science 9. So today we're going to cover lesson 7 on covalent compounds. So this will be in your notes package. I don't just now have an assignment for that, just wanted to give you some instruction and to show you some example substances, example compounds. So we'll get started. In Chemistry 11, you're going to learn two groups or two kinds of chemical compounds. One is, for today, is covalent compounds, and the other is ionic compounds. We use different language to describe these kinds of compounds, to describe their properties, because they're made in different ways. Looking at covalent compounds, we talk about particles of them being called molecules. In a molecule, you have a group of atoms joined together. They're forming a particle, which makes up a substance that has its own, what are called chemical and physical properties. So we're going to look at some of that today. The key vocabulary for you here will be the concept of a molecule, a covalent bond, and a hydrogen bond. So in a covalent bond, I guess one thing I showed you before is I showed you an example of ionic bonding. I showed you how an atom of, I think it was sodium that I went through, can donate an electron, and it can be received by a different element. I think it might have been chlorine. So there was a transfer of an electron from a sodium to the chlorine, sodium atom to the chlorine atom. We ended up with a sodium ion and a chloride ion. Remember the IDE at the end. We made sodium chloride, also called table salt. That's an ionic compound. The only reason that sticks together is through electrical attraction. So the sodium, once it's lost its electron, gets a positive 1 charge. Chloride, once it gains that electron, gets a negative 1 charge. The opposite charges are attracted to each other. Opposites attract. They're stuck together to each other by that electrical attraction, called electrostatic attraction, and that makes, when you take trillions upon trillions, or trillions of those together, you end up with crystals. I'm going to look more at ionic compounds later, but not a bad review already. Covalent compounds are different. In covalent compounds, you're dealing with atoms that neither of them is necessarily all that strong in their ability to either give away electrons or take electrons on. They're reactive, but they're not as powerfully reactive as, say, your alkali metals or your halogens. Although halogens can do this too. When you have two atoms that are not strong donators or strong receivers joining together, you're pretty much always going to get what's called a covalent bond. Instead of electrons being taken from one to the other to attract them by opposite charge, you get a bond where the electrons get shared. When electrons are shared, you're making a covalent bond. Now, one thing to realize about when this happens is that the electrons are not always shared equally. Sometimes one atom might be better at tugging the electrons away relative to the other one. Now, when that happens, you can think of it as the electron spending a little bit more time around one atom than it does around another. It's a little bit like that. When that happens, you know this by now, I think, that electrons have a negative charge, protons have a positive charge. So if one atom is sort of sucking in an electron a little bit more towards it than the other end of the molecule, one end of the molecule is going to be a little bit negative, the other will be a little bit positive. This happens really powerfully with oxygen. Oxygen is right next to fluorine on the periodic table. You might have noticed that. There's a connection there. The oxygen is also pretty good at pulling electrons. Much better at doing it than, say, hydrogen. So when you have a molecule that has oxygen and hydrogen in it, bonded to each other, oxygen is going to be a bit better at tugging that electron in its direction. making the oxygen end of that molecule a little bit negative. It's not ionic, but it's a little bit more negative than the hydrogen end. But opposites attract. As a result of that, you get some really interesting properties in substances that have oxygen and hydrogen joined to each other. I'm talking about hydrogen bonding. Some of you might have done that activity in the past where you took a penny and you put drops of water on it. See how many drops of water will fit on the penny. A lot of people are surprised that on a typical penny you're able to fit 32 drops of water. You wouldn't think it based on the size of a drop of water and the size of the penny. But the water is kind of piling on top of itself. Water does this because the water molecules are pulling together. Think of it like a crowd of people who are trying to not be moved by some other force. Everyone locks elbows together. Water molecules are a little bit like that by forming what are called hydrogen bonds. Let's look at what that looks like conceptually on a different scale here. In the notes, I say, show me a diagram with hydrogen bonds. You can probably find this on the internet, but here's what I made. What we see here is this. You know that hydrogen, you can pause the video now and I'll go back. You know that hydrogen and oxygen exist in water as H2O. You've probably heard H2O a million times. What that means, fire. That wasn't supposed to happen. Had to switch that off. Smelled good though. We'll get back to that later. What that means is that you've got two hydrogen atoms joined together with one oxygen atom. And it's kind of like a Mickey Mouse molecule. Oxygen in the middle, hydrogen, hydrogen. For reasons that you'll learn later, it's not like hydrogen, oxygen, hydrogen in a line. It's oxygen, the hydrogen's kind of sticking up like that with about a 110 degree angle. You'll get into that later why that is. But the bigger thing you need to know is that with that hydrogen being a little bit positive, and with that oxygen end being a bit negative, if two water molecules are close to each other, they will orient themselves so that the oxygen is kind of like a little bit closer to the hydrogen end. So you see in my diagram right there, I've got a hydrogen on a water molecule that's kind of forming a little association with an oxygen on a different water molecule. This is not a chemical bond, but it's a physical bond that's very important for understanding why water does what it does. All the crazy chemical properties that such a normal substance has as water. And one of them is this hydrogen bonding, where different molecules can be attracted to each other by the fact that one end is positive, another end is negative, and opposites attract, even if it's on a different molecule. Now, to be clear here, it's not like in a drop of water, the same molecules are always going to be doing that with each other. It's not like that. Water molecules are always moving around, but these associations are instantaneously forming and breaking a countless number of times per second for a countless number of particles of water that are there, but the hydrogen bonding is still there, and it's important, again, for a lot of why water does what it does. Hydrogen bonding is not unique to water, but it is strongest in water because water is made of just hydrogen and oxygen with that very unequal sharing of electrons involved. That's hydrogen bonding. What I also want to look at today is three different chemical compounds. Really all I want to show you is that compounds that are made with covalent bonds, molecules, have all kinds of diverse properties, and I want to show you conceptually kind of what they look like. There's three of them that I have in the notes, and I'm going to go through the properties with you here. This is the table we're going to fill in. So what is all this? All right. Ethanol is a molecule. It's also called alcohol. It's the same stuff in the drinks that your parents might drink, in vodka or beer, wine, or whatever, alcoholic drinks. So, black, carbon atoms. White, hydrogen atoms. Red, oxygen atoms. An ethanol molecule is a very simple molecule. There we are. Now, when you learn organic chemistry later, in grade 11, you're going to learn the rules for naming these things and the rules for their structures. So, we might say CH3, CH2, OH. And there's a structure for this ethanol alcohol right here. Now, the next one is sugar, sucrose sugar. This one took a while to make, but you eat it all the time. Again, it's made only of carbon, black balls, hydrogen, white, oxygen, red. But you might take it a little bit for granted that this is actually a very big, very complicated molecule, and your body has to have ways of using this stuff for energy. Because when you go for a run or do your exercise or whatever, you're using chemical energy. Molecules like this give it to you. Looking at it more closely, here's what we've got. We've got two parts to it. This part right here is a ring of 5. In that ring, one of the molecules, one of the atoms is oxygen. The other atoms are either directly joined to hydrogen, oxygen atoms with hydrogen, and they also have hydrogens on them. And here we have a C, H2OH. There is a bridge right here of an oxygen atom that joins it to another section, which looks kind of similar, except here, I'm trying to show it. Here you've got try it this way, that's better. Here we've got a ring of 6. You can kind of see that. In the ring we've got an oxygen atom, a carbon, carbon, carbon. So this second ring has got 6 parts. 5 carbon atoms, 1 oxygen atom. And again, here we have oxygens joined to hydrogens. Oops, forgot to put in a hydrogen right there. So it's a complicated molecule. If you Google sucrose atomic structure or molecular structure, you're going to get an image a little bit like this, a little bit like it. Again, this is a conceptual diagram or a conceptual model for sugar, the stuff that you are eating all the time. Now, it should come as no surprise then for what you already know, which is that sugar and alcohol look really different from each other. I'm going to get to the last one. I really like this one. This is called camphor. Notice at the bottom here, it's got a ring of 6 in this kind of weird like A-frame cabin shape right here. On top of that A-frame, we have a bridge of 1, 2, 3 carbon atoms joining the opposite sides of that 6 carbon ring. At the top of it, we have a carbon here with these 2 carbons sticking off from here. A whole bunch of oxygen, and oh, look what's going on here. One of the carbons has got a double bond to a single oxygen atom. You're going to learn more about this in Chem 11, so don't really worry about knowing any of the naming rules or anything right now. All I'm showing you is that when you take the simple atoms, carbon, hydrogen, and oxygen, and join them together, you can get an infinite number of possible outcomes. You can get the substances that you find in paint thinner or in tree sap, which have a powerful smell, and there's similar ones to them, like that are found in mint and phenyl aniseed. Molecules like this have a powerful smell and a low melting point. Molecules like this that are found in alcoholic drinks and in medical products. Molecules like this that you consume all the time and that are found all over the place in nature. So huge differences in size of the molecules, huge differences in their shapes, huge differences in how many carbons, oxygens, and hydrogens there are. So it won't come as any surprise that when you take this stuff and you look at the actual chemicals in front of you, you're going to see they look really different from each other, and they have a lot of different chemical and physical properties. There are some things, though, that kind of unify them, and I want to look at that a little bit with the activity. So I've got some of these actual samples, and I'm going to show them to you. This is ethanol. This molecule right here is in here. It's a clear liquid. That much is obvious. We're going to fill in this table as we go. This will be harder to see. I'll try and hold it up a little bit. You can kind of see that. These are crystals. You can maybe hear that. Crystals of sugar. If you want to see more sucrose sugar, just look in your kitchen cupboard. The next one is more difficult to get your hand on. And that is camphor. Flammable substance found in tree sap. Part of why pine trees burn so hot in a forest fire. You won't be experiencing this. I am. I don't know if anyone of you has ever tried that stuff called Tiger Balm. You know, if you've got like a sports injury or something like that, and someone might like rub it on sore muscles. I don't know why it would work, but anyways, camphor is in Tiger Balm. I think Tiger Balm is some kind of mixture or some sort of wax with camphor. So when I smell this, it smells exactly like Tiger Balm because this molecule here of camphor is in it. Notice this. You could say, a lot of people looking at this would say that it was white. In reality, what we've got here, if you looked at a microscope, you would see that just like sugar, this is clear crystals. Very similar chemically to sugar. In its appearance, it's very similar to sugar. So for the sugar, we might describe its texture as grainy or crystalline. Here, listen to this. I'm crushing the crystals of sugar. We'll get to that later. The camphor, it's more of a gummy type thing. You can't really see this, but the crystals kind of stick together. It's still crystalline in its shape, but the crystals are sticky to each other. Viscosity, this isn't working out so well. Let's see what we have. I wanted to make these into their liquid forms so I could show you whether or not they would flow. This would be a fail. And I think, here's why, in my opinion. For a start, we already have ethanol as a liquid, so that's no problem. But in here, I was trying to melt the camphor to see if I could make it flow. to see how viscous it was or how goopy. Viscosity is a measure of how much something sloshes around when it's in a liquid form. Here, earlier on in the lesson, I was thinking, I was sort of starting to smell something. And yeah, it was a very pleasant kind of baking type smell, but that's not good in the chemistry lab. What that means is that the sugar I was trying to melt to look at its viscosity has gone and burned. Sugar is really difficult to melt. It's much more likely just to break apart as a molecule. Let's see if we have any flow here. All right. Looks like what's happened here is that it did melt, but at the same time as it melted, because I put this in as crystals just at the bottom, at the same time as it melted, it also started to break apart chemically. There you see that. We've got bubbles. It's probably starting to burn. This beaker is going to be pretty hard to clean up. Well, you can see right here, it's actually kind of cool. This is the camphor. What's happened here is that camphor has quite a low melting point, but it also has a very low boiling point. So when I put it in this hot plate, it didn't burn up. That might have been bad. What it did do is it evaporated at a very low temperature, which is hardly surprising for something that smells so powerful that it has a low boiling point. But it also condensed very easily. So look what's happened. Oh, this is cool. What's happened is we've got all this evaporated camphor that then condensed on this beaker that I used to cover it. I was kind of worried this might happen, and so that's why I put a beaker on top, because I didn't want to fill the whole room with a camphor smell. So it's condensed here rather than in my nostrils. I'm going to risk it a little bit, take that off. It's actually kind of cool. See this here? The camphor is recrystallized. Keep in mind, I took a chunk of it at the start and I put it in the bottom. That's all gone. It's all evaporated, and in fact, you can also see there. Look along the rim of the beaker. It's not only just reformed, condensed. New crystals, brand new crystals of camphor have condensed in the air while I've done this exercise. There's been no physical change here. There's been no chemical change. It didn't react chemically. It just evaporated and recrystallized. So we didn't get to see it as a liquid. So we don't know if it's viscous or not. Some of this table we won't be able to fill in. Here's what I do want to fill in. Solubility and conductivity. This you can do at the same time. Solubility is how well something dissolves in water. If you take some water and put some of the substance in there, and it starts to go away, disappear into the water, it's soluble. If it doesn't, if it just sticks to the bottom, or mostly sticks to the bottom, we say it's only partly soluble or not soluble at all. Solubility is how well something fits into water or dissolves into water when you add it to water. Conductivity is a measure of how well something conducts electricity. I'm going to try and measure the conductivity of these as solids and then look at their conductivity when they're in a solution. So I got the conductivity right here. We've used this a whole bunch of times. Got water. And I got my substances. So I'm going to take some of the sucrose. Actually, let's start with ethanol. Now, ethanol is already a liquid, obviously, but it can still form solutions or maybe not form solutions. If I were to mix this with water and it was just to make this cloudy liquid mixture, I would say that ethanol is not soluble. But if instead I mix it with water and I find that, hey, it disappears, then we would say, yes, ethanol is soluble. You can kind of see what happened there is it's kind of like filmy a little bit. But as I stir it around, that disappears, which is hardly surprising. In a glass of wine, you don't see cloudiness of ethanol in one part and water in another part. No one would drink wine if it did that. In a glass of wine, we see that it's clear. It's got a color, but it's clear. Water will pass through. That is our ethanol solution. I'm going to keep that. In fact, right now, I'm going to do conductivity. I'm going to do conductivity of water, tap water, and then I'm going to add a bit more ethanol to this for good measure. Measure its conductivity as a solution and of water as a solution. Water registers as non-conductive. Remember that one part? I've got it again. Ethanol measures as not conductive. I'm going to try pure ethanol. Not conductive. Here, I'll show you what I mean. This means not conductive. We're done with the ethanol. Next, we're going to look at the sucrose. Why not? I'm going to look to see if solid sucrose is conductive. Now this would be difficult at the best of times because, of course, there's a lot of air between the crystals of sucrose. Ideally, we'll be doing this as a liquid, but obviously we can't because it's really difficult to melt sucrose. The answer is no, it's not conductive. Now I'm going to try and make a solution with the sucrose. I'm going to add some water to the beaker. Add a bit more of the sugar. The answer is still no. A sugar solution does not conduct electricity. Camphor. Keep in mind, we don't yet know if camphor will even dissolve in water. I'm going to take some of this here. Here's some water. So far it's just sitting there. I'm going to get a stirring rod, see if I can dissolve it. So I'm breaking this off. What I'm seeing is that the crystals are separating from each other, but they're not really disappearing in solution. I'm going to keep trying. Still not really happening. You know what I'm going to do? I'm going to do, here's what I'll do. I'm going to first of all test to see if solid CAM4 is conductive. Answer is no, it's not. Next, I'm going to write some of this on the board that we've learned. You guys can fill in your table. Also, I'm going to take this and I'm going to put it on the hot plate. Figure out where we're at. Ethanol. Obviously, you saw that was a clear liquid. Well, you saw it was clear as its color, and its state was liquid. Sucrose, clear, or you could say white, and its state is solid. Camphor, just like sugar. Looks like sugar, but it's nothing like sugar in its other properties. Is clear, or you could say white. I'm going to try to write better. And it's also a solid. Malleability, remember that's the ability to pound something into sheets or not be able to pound something into sheets. Here, I'm going to shift this over. For something to know if something's malleable or not, you have to be able to make it into a solid. I don't have a freezer that'll freeze liquid nitrogen. I can't freeze the ethanol, so that's not available. The sucrose, not malleable. The crystals just break apart. The camphor also, not malleable. Keep in mind, this is a way that this is something we do expect metals to be. We expect it to be possible to hammer a metal into a shape. These nonmetals or substances made with nonmetals, with covalent bonds, you can't hammer them into sheets. I'm just going to put Na for the texture, or you could, I don't know, I guess you could put watery as a description for ethanol as its texture. Sucrose and camphor are both crystals. That's probably the best way I would describe their texture. Viscosity, honestly, I would say watery again as the viscosity for, or actually, you know what? No, here's what I'll do. Similar to water. The sucrose, I made caramel. It burned, so the viscosity was unavailable. And for the camphor, well, I made new crystals. It was really cool, but we don't know the viscosity. Now with sucrose, you might remember that you sometimes have pancakes for breakfast, right? Pancakes have got a lot of sugar. You'll be putting maple syrup on the pancakes, right? That maple syrup has got a lot of sugar in it. So solutions with a little bit of water and lots of sugar are very viscous. Conductivity, no, and well, we aren't there yet for camphor. We don't know if what it's going to do. We're going to come back to that. But ethanol and sucrose, not conductive. Remember, metals are conductive. I can't think of any exceptions. These are compounds made of nonmetals. They're not conductive. Melting and boiling points. You guys are going to do some work. I'm going to have you find the melting and boiling points for ethanol, sucrose, and camphor on the internet. They're all there. Hardness. Ethanol is not available, because we had it only as a liquid. Both sucrose and camphor were soft, because after all, I was able to crush them with my fingernail. The solubility, ethanol, yes, it's soluble. Sucrose, yes, it's soluble. Metals aren't like this. Metals aren't soluble. Camphor, let's go and see if any of the camphor is dissolved. And then we can test its conductivity as a liquid, and we're done. My assessment is, wow, the crystals are still in there, but they're smaller. I'm going to say it's slightly conductive. Let's see, I'm going to say it's slightly soluble. And last here, conductivity. Again, it's a no. A solution of camphor, this weak solution of camphor, smells really nice, but it's not conductive. So we'll say for the camphor solubility, I don't know, we could say a bit. A bit soluble. And that's it. So I hope that what you've seen in today's little activity is that covalent bonds are made between nonmetals that are more, and in a covalent bond, electrons are shared. They're not transferred totally from one to another. Covalent bonds are typical for nonmetals like the ones we looked at here, molecules made of carbon, hydrogen, and oxygen. That there can be all sorts of different sizes and shapes of molecules made from nonmetals. You could make a city out of Lego. It's the same way with covalent bonds. You can bond any molecule, any atom next to another atom next to another, and so on, and make gigantic molecules. These are the molecules of life. You've learned about hydrogen bonds that form especially between water molecules and account for some of the weird properties of water. And you've done a little survey of 3 very different chemicals that have covalent bonds and seen how their properties are different from each other. So, a bit of a longer lesson, but I have no assignment with it. It's just, I hope that you found some interest out of that.